Okay, in this video we're going to talk about Unit 11, Objective 1, Infinite Geometric Series. So back in Algebra 2, and you might have done this some in pre-cal, you talked about sequences and series. Now a sequence was just a list of numbers. Any list of numbers is going to be a sequence. And a series is going to be the sum of all of those numbers in a sequence. There are two types of sequences and series that we look at very closely, and those are arithmetic and geometric sequences and series. An arithmetic sequence is a sequence where the numbers change by a certain common difference that we would call d. So you're going to add that number each time. So like 1, 3, 5, 7, each number is going up by the same 2. Now a geometric sequence is going to be a sequence in which the numbers change by some ratio. So we're going to multiply by the same number each time. So instead of adding 2, we could multiply it by 2. So 1, 2, 4, 8, and so on. Now what we're going to be doing in 1101 is taking an infinite geometric series. So we're going to take one of those series where we're multiplying by the same thing each time, and we're going to add up infinitely many terms and see if we come up with an answer. Now the answer, if we get an answer, that's going to be called our sequence is converging, and if we don't get an answer, we're going to say our sequence, or our series rather, diverges. So a couple things that we need to think about, or we need to remember. For a geometric sequence, so we're not adding all of these things together, but we define a geometric sequence by the following: a1 times r to the n minus 1 power, where a1 is your first term in your sequence, r is what you're multiplying by each time, and n is the number of terms. Now if we want to find the series for that, so if we want to add up all the terms, we use what's called a sigma notation. So the Greek letter sigma, and that n equals 1 at the bottom means we're going to start with 1, and n at the top just means how far we want to go. But we're going to change this a little bit. Since we want to talk about infinite geometric series, we're going to start with n equals 1, and then we're going to go all the way to infinity. And we're just going to take that sequence definition, and that's what we're going to find our sum of. So if you don't remember what this layout here means, is we're going to take n equals 1, we're going to plug 1 in for n, get an answer, plug 2 in for n, get an answer, plug 3 in for n, get an answer, add all those things up, and that's going to be our sum. Now, this is one way an infinite series can look. Another way would be the sum from n equals 0 to infinity of a1 times r to the n instead of the n minus 1. Those are the two things that we're going to look for infinite geometric series. We're going to try to find a way to write our sequences or our series this way so we can jump straight to our answer, because we're going to say the infinite series is going to converge to the value a1 over 1 minus r if and only if the absolute value of r is less than 1. So if we find what we're multiplying by each time, take its absolute value, if that absolute value is less than 1, our series is going to converge, and it's going to converge to whatever a1 divided by 1 minus r is. So we're going to do a couple of examples, and then we'll call it quits on the video. So we'll start really basic. We'll say, does the following converge? So we'll start out real simple. We'll start with 1 minus 1/2 plus 1/4 minus 1/8 plus, and so on forever. So the ellipses mean we're going on forever. So we have to think, all right, what is my a1? So a1 is just our first term, so a1 is 1. What's my common ratio? What do I multiply by each time to get from one term to the next? Well, to go from 1 to negative 1/2, I multiply by negative 1/2. If I multiply by negative 1/2 again, I get my 1/4. Multiply by negative 1/2 again, I get my negative 1/8. So that tells us that our common ratio r is negative 1/2. We have to check, is the absolute value of r less than 1, and it is, so we know we're going to converge, and what this is going to converge to is 1 over 1 minus negative 1/2, which is going to be 3/2. Oh, sorry, 2/3. I forgot to do 1 divided by. So it's going to be 2/3 is what this will converge to. So if you follow that pattern out to infinity, your sum of all of those numbers is going to be 2/3. Alright, so let's look at another way these things can look. Same thing, does the sequence or series rather converge, and what will it converge to? So we'll say the sum from n equals 0 to infinity of 5/3 to the n power. So if we think about the two sigma notations that we had before, this looks like one of them. We have n equals 0, we have an n power. So we got to think again, what is a1? Well, in this case, it's going to be 1. And what is r? R is 5/3, but 5/3 is greater than 1, so this is going to diverge. So what diverge in this sense means is we're not going to be adding smaller things, we're going to be adding bigger and bigger numbers, so our sum is going to grow to infinity. So divergent series here because r was greater than 1. Now, AP is not going to be that nice to you. AP will give you something like this. The sum from n equals 1 to infinity of 9 to the negative n plus 2 power times 4 to the n plus 1 power. And they're going to ask, does that converge or diverge, and what does it converge or diverge to? So we have to look at what we're given. We have an n equals 1. So if we think back to the two series I gave you, if we have n equals 1, we want an n minus 1 power. So we have to kind of mess around with what's inside the sigma notation in order to get a single number to the n minus 1 power. So what we can do is we can kind of rewrite the inside, and we can say 9 to the negative n plus 2 is the same thing as 9 to the negative n minus 2 power times 4 to the n plus 1. So now we have a negative exponent. We can rewrite this as 4 to the n plus 1 over 9 to the n minus 2. Now remember, we want an exponent of n minus 1. So we can rewrite this part, the 4, as 4 to the n minus 1, because that's what we want. Now, I originally had a plus 1, so I need to add 2, because 2 minus 1 is going to be 1. So I'm not really changing the value, I'm just changing what it looks like. Instead of having n plus 1, I'm going to go with n minus 1 plus 2. Similarly, on the bottom in our denominator, we can say n minus 1 minus 1 for our exponent. Then we can play around with our exponents a little bit. We can say 4 to the n minus 1 power times 4 squared over 9 to the n minus 1 power times 9 to the negative first. So we can now rewrite this as 4 to the n minus 1 over 9 to the n minus 1 times 4 squared times 9, right? Our negative 1 is going to bring this up top. Since we have the same exponent for our 4 and our 9, we can write this as 4/9 to the n minus 1 power times 144, because that's what 4 squared times 9 is going to be. So we can now rewrite this whole thing, our sigma notation, as n equals 1 to infinity of 144 times 4 over 9 to the n minus 1 power. We now look at, we now match what we looked like before, what we needed. We have that n minus 1 power. The absolute value of 4/9 is less than 1, so this will converge. and it's going to converge to whatever 144 divided by 1 minus 4 ninths is. And I'll leave that simplification up to you. But that's kind of like what AP is going to give you on a question like this. You're going to have to manipulate your series and try to figure out how to write this as something to the n power or something to the n minus 1, depending on where your series starts. So let's look at one more, and then we'll call it quits on this video. So again, same idea. Does it converge? If it does, what does it converge to? We're going to go from 0 to infinity of negative 4 to the 3n power over 5 to the n minus 1 power. So again, we have nothing given to us, very straightforward. We have to manipulate. If we look, we're starting at n minus 0, so we want our exponents to be of n. So right now in my numerator, we have to the 3n. So if we kind of mess with our exponents a little bit, we can rewrite that as negative 4 to the 3 to the n power. And just like we did before, we can say 5 to the n times 5 to the negative first power. So we can rewrite this part as negative 64 to the n times 5. So that 5 is from the denominator over 5 to the n. So now we have our n powers. So we can go ahead and rewrite our sum as negative 64 over 5 to the n, and then that 5 can go out front. So once again, we have to check, is the absolute value of negative 64 over 5 less than 1? It is not, so this is going to diverge. So that'll do it for this video. We will see you in the next one.